But now I want to know more about what's going on. I want to know whether onset affects the area under disease progress curve, whether rate affects yield. Are these variables affecting one another and affecting what I am seeing? So one of the things I can do, maybe I should just cut and paste this again, or have I still got it here? No, I haven't. Give me a second, I'll just close all these windows. Come on. And I just want to do that again just to make sure everything is cleared. Okay, and what I'm going to do is I'm going to take my table here now. And put it back in NCSS. Oh, I have pressed the wrong button. That's normal. It's a problem when you're trying to be high speed. It's so much easier when you've got a mouse in your hand and you are sitting behind your desk. You've got somebody, you can shout to your students, please, coffee. I just want to get these columns out. Right, and I need to move that into my view. Right, so I've now got my spreadsheet there. I now want to work out, is there a relationship between the different variables? Now yesterday, you know, we spoke about correlation coefficients. Very simply, I can go to analysis, correlation, the correlation routines. I wanted to work out a correlation matrix for me, and I want a Pearson product moment. I don't want ranking correlation. I can do ranking correlations as well. They're the Spearman ranks. Okay. But in this case, I'm going to just see if there's a relationship between the variables, and I can say run. And you can immediately see, obviously, that's a coefficient of 1. Onset versus rate. There's a negative relationship, and it's significant for the degrees of freedom. And you can then, and the negative value is telling me that the faster the rate, okay, well, there's a negative relationship between rate and onset. In this case, yeah, sorry, it's telling me that there's a negative relation with rate and yield. So in other words, the faster the rate, the more disease is going to develop, the more the yield is going to come down. Area under disease progress curve, onset and area under disease progress curve is a negative relationship, significant. In other words, the later the onset, the less the area under disease progress curve, and you can start making deductions about the relationship between your variables. Okay, so I've got that on my spreadsheet as well. Yeah, so it's a very simple analysis if you have a basic. The critical R value here is 0.63. You can see I'm pretty borderline there, but most of them are significant. Okay. And that value you would look up for the degrees of freedom that you have, 8 degrees of freedom, in a correlation table that I showed you yesterday. So that very simply is the relationship between the variables. Now all that tells you is that there is a significant relationship between the variables. It doesn't quantify it. So I can go a step further and I can use a regression program, and you can do this very simply on Excel if it's linear. Okay, I'll plot my values on Excel. I can then do a right click, add a trend line, ask it to display the variables for me, and I want a linear model. That's the default. And I press close, and there I've got And now I have the relationship between disease onset and area under disease progress curve quantified. In other words, if you have a look here, for every day that onset is delayed, my area under disease progress curve comes down by 0.51 units. And my unit here is days. So in other words, the area under disease progress curve is coming down by 0.51 per day that the disease is delayed. I can now quantify the relationship between area under disease and disease onset. I can do the same for the rate. And you can see here, okay, R square is a little bit lower, variation is a bit higher, but essentially the rate, as the rate increases, so my expected area under disease progress curve is going to increase, and there's a rate coefficient which is going to tell me how fast that is going to happen. Okay, so as my rate increases, for each rate unit increase, I'm going to have an increase in the area under disease progress curve of that value. And so we can carry on. Area under disease progress curve versus yield. You can see that yield comes down as the area under the curve, and onset versus yield, the earlier the onset, the greater the yield. And you can then very simply, with these regression analyses, look at relationships. Now, all this is coming out of my simple randomized block design. Okay. So by applying the right statistics, whether it's modeling, whether it's correlation coefficient, whether it's regression coefficient, you can reach numerous conclusions about what is actually going on in that soybean rust system and the reaction of varieties. So from my analysis of variance, lines differ in disease onset. Line 1 was 55 days, line 3 was 84 days. The rate of disease development differed significantly, also from my analysis of variance. Okay, line 3 was the lowest and line 7 was the highest. The total disease levels differed based on area under disease progress curve, and you can decide which lines differ from one another, and yield differed. Okay, so you've got the line response to these different variables. There was a highly significant relationship between disease onset and area under disease progress curve and yield. I got that from my regression analysis. So obviously the variety or cultivar line that has the latest disease onset is going to have the lowest area under disease progress curve, and it's going to have the highest yield, right? The later disease onset resulted in, okay, there you have it. A similar relationship was recorded with rate of disease increase. Okay, you saw that from the graphs. Now, here's an important thing. Since the lines differ in terms of disease onset and rate of disease development, and because of the respective effects on disease and yield, you can decide how important these are as a selection criteria. So in other words, when I'm going and selecting lines, obviously I want to get the ones that have a later onset, and I want a slower rate of disease development. And the effect on area under disease progress curve and on yield, I can determine from my regression graph. So I can decide the importance of that. Okay. So now my regression graph, my selection criteria, my cultivar response are all integrated into one single story. Right. And I can even go a little bit further and say, right, this later onset, and this is what we've been trying to do. We haven't been that successful, but what is the underlying physiology behind these observations? Is it something like antifungal proteins? Is it like phenols, flavonoids? In other words, the one retains its antifungal proteins for longer than the other one, you know? Or is there something that is switched on at a certain critical stage of the host development? So you can then hopefully get a selection criteria like rating for chitinases at a certain critical point, and that could become a selection criteria as well, which is less objective than being in the field. You can sit in the air-conditioned lab with a white coat and do it. Okay, so these are the kind of things that from a simple randomized block design and applying correlation coefficients, applying regression coefficients, applying disease progress curves, I can get a lot of information about what is going on in that disease system. The programs I use, as you saw, they're very basic programs. I didn't even have to go to programming in stat graphics. I could use sort of Windows or user-friendly programs to reach all those conclusions. Okay, so by integrating your analysis of variance, your t-tests, your regressions, your correlations, you can get a pretty good picture of a whole disease system. Okay. Does that make sense? Right, and it's simple. I mean, it took me 2 minutes, not quite, a couple of minutes, okay, to give you, from a few numbers that I collected in the field, a whole story about a disease system. Okay. So that is the value of applying statistical techniques to your data and then getting a picture of what's actually going on. And the more you do it, the better the picture. It's like a jigsaw puzzle. You put all the bits together and eventually this whole picture emerges. So that's just a few examples of how we use stats to analyze our systems, whether it's a yield system, an agronomic system, fungicide spraying, disease evaluation, it doesn't matter. The principles stay the same. Okay, so I'll stop on that note and leave it for questions if there are any.
Yeah, I have